So thank you again, Nikhil, and all of your team for this kind of invitation. Today's session is talking about the production chemistry in oil and gas industry. This is a very crucial topic and has been like a hot topic for decades. I'm going to start by briefly introducing myself. I know he just did that now. My name is Abdullah Hussein. I've been in the industry for 16 plus years, focusing mainly on production chemistry stuff such as lab work, solids deposition, emulsions, corrosion, chemicals, microbiology, all this kind of stuff. Recently, I moved to Canada. I was doing consultation and training for some service and operating companies, which encouraged me to start my own platform. It's called Chemistry, where we do training, consulting, and also a little bit of fluids modeling. 2 years ago, I published a book. You can see a picture of it here on the right, talking about solids deposition in oil and gas fields, how to do risk assessment, how to monitor, analyze, characterize them, how to manage them in so many different ways, chemical, non-chemical, operational. There's a few chapters also about production operations and fluids properties, pigging, chemicals, how to deliver them. So feel free to check this out on the publisher's page. Our agenda for today is very rich. We are going to start by introducing the production system, and then we will move to the concept of flow assurance. And then we will move to the origins of production chemistry issues. Where are they coming from? And then we will jump to the main solids in oil and gas fields, specifically scale, hydrates, paraffins, asphaltenes, naphthenate, and also other types. And then we will move to another topic, the phase separation problems, including the foam, emulsions, and sludge. And we will also see the direct connection between the solids and the phase separation problems. I also have seen a lot of people talking about solids are connected, or there's like a strong connection with corrosion. And of course, this is true, but there's also a strong connection between the solids and the phase separation problems. So this is our production system. The main components you see here is that reservoir. This is the heart of our system. This is where the fluids are being pumped from the system to the surface, and also some fluids can be pumped down into the reservoir. And then we have the main vein for our system is the well. This is where we push the fluids to the surface. At the surface, first thing we will see is the wellhead, which is a bunch of valves assembled together in a fancy way called the Christmas tree to manage, the flow of the fluids to the surface facilities, and also to manage the workover operations, the well intervention, the treatments that we inject down into the reservoir, all this kind of stuff. On the surface also, we find the flow lines. And then we have the treatment facilities. This is where we separate the different phases, the oil and gas, and then we send it to, the sales and the final terminals. And also we have the water that we treated and then we dispose of it, or maybe we can re-inject it back into the reservoir. What do we want from this production system? Basically, we want the fluids to be flowing smoothly, economically, and in a safe way. And this is where flow assurance is actually been used. Flow assurance is basically trying to assure that you will have a smooth and economic and safe way of flowing your fluids from the reservoir, from the first point in your system, to their final terminals. And you will do this by managing a bunch of different challenges as much as you can. These challenges can include scale, hydrates, wax, asphaltenes, corrosion, all this kind of stuff. And I'm saying you have, or we try to assure we have a smooth flow as much as we can, or as much as possible, because there's no perfect system. There's always something. You might have 1, 2, or 3 of these, or you might end up with like all of them if you're lucky. I mean, if you are actually unlucky. I mean, on the other side, you will be lucky because you will get a lot of experience by dealing with all that stuff, and you might hire some flow assurance specialist. He will solve your problems, and then you will pay him money, so he also can be lucky. And then the operating companies that you work for, they also they will restore their production, so they will also be lucky. So there might be a slim chance that everybody will go home lucky. So anyways, this is what we do in flow assurance. We try to tackle and manage all of these issues. You can look at the flow assurance as if it is, a healthcare system. In healthcare system, whenever you have a patient or something, what they do there, they pull samples from the patient and do analysis like blood work, urine analysis, all this kind of stuff. And they also might do some CT scans, X-rays, all this stuff, and do diagnosis of the problem. And then they give you medication for treatment. And then after that, they try to monitor your case and see if you are getting better or not. So if you're getting better, then you're good. If not, they might need to, reassess the whole problem from the beginning. It's the same thing in a flow assurance people. They do the same exact thing, but I mean, in so many different ways. So we pull samples from the production system, we do analysis, and then we do risk assessment. And we do risk assessment in so many different ways. So we do this first thing by do modeling. That's the main thing. And we do modeling for so many things. For the reservoir modeling, we do modeling for the multi-phase flow, CFD, to see, how fluids will flow, the sizing of the pipelines, the sizing of the production equipment, the pipeline's layout and all that stuff. We also do modeling for the solids, for every kind of solids, for the scale, for the asphaltenes, for the waxes, for the hydrates, for all these kind of stuff. We also do modeling for some of the operations like the pigging. We also do modeling to see if the fluids are going to be corrosive or not, for the material selection and all that stuff. Another way of assessing the risk in the flow assurance is by doing experimental studies to see if there is any risks of problems in the production system or not. We also do the risk assessment by learning lessons from similar case studies, or the analogy, using the analogy between the different cases. We do risk assessment by so many different ways, but the ultimate result is we gather all these data and put them in a big risk matrix and see what might go wrong in our system. Based on this risk assessment, we start to do, the treatment, either chemical or non-chemical or operational, based on your capabilities. And then after we do or apply the treatment, we start monitoring our system and see if the treatment is working or not. If it is working, then everything, we will keep monitoring. If it's not working, then we might need to go back and start the assessment from the beginning, doing fluids analysis and all this stuff all over again. And like in a healthcare system, whenever you have like a newborn or something, you have to watch him all over the time from day one. You watch his weight, you give like a schedule for his vaccines and his medication, you do checkups with the doctor to make sure that the baby is okay. The same thing, flow assurance, they think the field is their baby. They have to do the flow assurance plan, the risk assessment, and all this stuff from the earliest stages of the field development. They call it the feed, or the front end engineering design. This is where you should start planning your flow assurance stuff, so that if anything goes wrong, you will tackle it and manage it and at the earliest stages. And this will take us to this picture on the right. We are going to break our flow assurance strategy based on the stage of your production. So if you are still in the initial stages, you will do a lot of fluid sampling and modeling, so that you will have like initial scenario or initial concept of your system. And then you will use the data from that, and then you will go to the next stage and the development. You will get more samples, you will do extensive modeling based on other findings, and then you will start your initial concept. And then after this, based on that one, you will start production. And then in the production phase, you will get more access to the fluids. You will get more, capabilities for the modeling. And then you will get the monitoring gears and everything, so you can watch your system in action. And then you can take, active or proactive actions to make your system working properly. And as I said, based on whatever stage you are in, it is always really, really crucial to start the flow assurance at the earliest stages. I'm going to give you two examples why this really matters. So one of the most common thing in the production system is the material selection. And it is well known that you select the materials based on so many assessments. One of them is the corrosivity of your production fluids, but also you have to check the material selection based on the treatments that you are going to inject into the system. I'll give you an example. If your system is vulnerable to naphthenate soap or something, then you might need to do the treatment using acids or injecting acidic demulsifiers. And this will require you to select the material that will be corrosion resistant. So you do not select the material just on the corrosivity of the production fluids, but also based on the treatments that you might inject into the system. Another example, if you did the risk assessment and it showed that you might have wax problems or gas hydrate problems, that might give you the indication that you might need to use heating gears like insulation or direct heat or stuff like this. So these need to be installed into the system from the day one to avoid, unplanned shutdowns, or if you're gonna go like do modification for the system design or anything like this. Specifically, if you're working in like a subsea field or something, one of these complex fields, the problem will be even worse. So flow assurance, we have been using it for decades, from the day we started actually production in oil and gas fields. But like using the term flow assurance, we just started using this in the 90s or in the late 80s. But we have been using it all the time. And we advanced in it like big time. So whenever we had a problem back in the time, we were just trying to avoid the problem by, operating outside the window that might cause the problem, or maybe, we will just increase the flow rate. So it's going like, strip the solids from the pipeline, avoid any accumulation of solids or anything like this. But then we advanced in our studies. We had the codes and the models to model the problems. We had chemical methods and non-chemical methods. So that gave us the ability to design a management plan for each problem, a management plan for scale, a management plan for asphaltenes, and so on. But then we keep advancing, and then right now flow assurance is actually will do a full field development from A to Z, from the early stages of field development to the last stage of field like an abandonment. And all of the flow assurance, if you go back into the core of it, you will see that it is based on two basic things: the fluids chemistry or the production chemistry. This is our main topic today, and the fluids physics or the hydrodynamics. And this is also like another big topic. But that also doesn't mean that only people with chemistry background are the only people are going to work in flow assurance. I've seen people in mechanical engineering, civil engineering, geology, all kind of stuff, and they are not just experts in the industry, they are giants in the industry. And this is also really important because the flow assurance is not relying on just one person. It is actually a team with different backgrounds, education, specialties, because we use a lot of technologies to apply the flow assurance. We use operational technology, we use hardware, the pipelines manufacturing, and the sensors and the designs and all that stuff, the software. Those people working with the theoretical and empirical formulas to give us models that can predict what can go wrong. The chemical technologies, wide range of chemical technologies, the thermal technologies, the physical technologies that we use for the sensors, metering systems and all that stuff, biological technologies as well that we use. So as you can see, there's different backgrounds here, and all of these has to pitch in so we can have a solid team that can do the flow assurance in a good way for the full field development as we mentioned. So we are going to move to our main topic, which is the production chemistry. Where our production chemistry stuff are coming from? What is the main source of them? The main source is the system itself. How did that happen? You can think of this if you go back to your production system. So we have the fluids, oil, gas, and water. They are entrapped in the reservoir for millions of years. And then we came later on and we started production. What happened is we disturbed the thermodynamic equilibrium. that these fluids had for millions of years. Once we start production, we just disturbed all that. And then we add stuff to the system, like inject water, inject gas, inject chemicals, all this kind of stuff. And this also complicates the problem. So these fluids and this system wants to go back to another thermodynamic equilibrium. It just wants to be stable again, because thermodynamic equilibrium means stability to them. So they want to go back to this thermodynamic equilibrium. And this happens by a bunch of different reactions between the different components of the system under the continuously changing pressure, temperature, pH, and hydrodynamics. So this is the main source of these. It's the reactions between the different phases under the continuously changing parameters. So what phases we have here? So we have the reservoir rocks, and then we have the fluids. So we have the gas, the oil, the water, the injected gas, the chemicals, all this stuff. We also have the steel. This is the material of construction. We also have the microbes or the microorganisms, all that stuff. All these are the main components. And what are the main parameters? So we have the temperature, we have the pressure, we also have the pH, we also have the hydrodynamics of the system. So all of these will react with each other under the changing, parameters to develop new phases and cause like new reactions that will cause the production chemistry issues. So you will see like a zone or a phase for the asphaltenes, another one for the wax, another one for the hydrates. You will see a zone where, scale can form, all this stuff. So let's put this all together in a big table and see how this will go. So we have the different phases and the different parameters here. And I just selected a few of these to see how bad things can go. So for example, if the gas reacts with the water at very high pressure, low temperature, then we will have gas hydrates. The oil can react with the injected gas, either it's like CO2 gas or gas left, and then this will cause asphaltene problems. The oil can react with another oil if they're not compatible together, will cause another asphaltene problems. The oil might itself drop off the asphaltenes if its pressure fell below specific limit. The oil might drop off the waxes if the temperature fell below specific limit. The oil might react with the water and cause emulsion or soap. The water might react with another water if they're not compatible, and this will cause scale. The water might just by itself, it's called self-scaling water, under the changing pH, temperature, and pressure will cause scale problem. The treatment chemicals, I know we inject them, to treat the production, make everything work smoothly, but sometimes they might not be compatible with the system. So they might react with the gas, the oil, the water, or with the steel pipes, and then they might cause corrosion or deposits. We will talk about this later on. We also have the rocks, the reservoir rocks. They might react with the gas, the oil, the water under the continuously changing pressure, temperature, might cause deposition, sand production, fines migration, clay swelling, all this kind of stuff. And then the metallic structures, the pipelines and the equipment, these might react with the production fluids. And then the main thing here will be the corrosion. And then we have the microorganisms. These little bugs will harvest their own nutrients from the production fluids and then might cause a corrosion called MEC, or the microbially influenced corrosion, or some sort of deposition, either the biofouling or the biomineralization. So you see, there is a bunch of different ways of these components to react with each other and cause a damage to your system. As I said, you might have 1, 2, 3, or you might have all of them. So what you should do as someone that works in a field that is interested in flow assurance is to make like a table similar to that and see the different phases in your system, the different temperature ranges and pressure ranges, and see, what might react with what, with actual data, your actual data for the pressure and temperature. Put this in your, control room or in your office. If everything goes good, no problems, then you can turn these little circles from red to green. If something's wrong, you just can't keep the red one and keep tracking it until you control everything. So our first thing that we're going to talk about today is the solids deposition. How many solids you think can form in an oil field? So many. So Here I put 9. So we have the scale, sand and fines and clay, gas hydrates, diamondoids, pseudoscale, biofouling, naphthenate, asphaltenes, paraffins. And there is a potential 10th one, the elemental sulfur. So the S8, this is the elemental sulfur. So if you consider it part of the mineral scales, some people consider it part of the mineral scales because it's a mineral eventually, then this will make these 8. But if you consider it a specific type due to the way it actually precipitate, then this will make your solids 10 types of different solids. And this is not everything, because in the mineral scales themselves, there's like tens and tens of these with different properties, different hardness, different solubility, different way of mitigation, which complicates the problem and make you in a really, not a good position. Where solids can form, everywhere and anywhere in the system, in the injection side and the reservoir and downhole and the tubing and the wellhead and the main production header and your production facilities and even in the final terminals, which makes the problem like hell for everybody. What are the main problems solids can cause? Lots of problems, lots of them. And the ultimate result is production decline, loss of money. But the main things I'm going to talk about is the formation damage. This can happen in your reservoir. Once this happens, this is going to, it'll be hard to restore the formation after that. And even if you restore it back, it might not be the same, productive as it was. We also have the flow restrictions and blockages. We also have the equipment damage, including flow meters, separators, pumps, heat exchangers, heaters, everything. Every equipment can get fouled by the solids, and this will decline their performance. You might need to go and shut down to maintain the your equipment, and you also might need eventually to maybe like replace it with a new one. Other problems by the solids include, they can induce other production chemistry problems, such as the emulsions that we have here. So the solids can stabilize emulsions by so many ways. We will talk about this later on. Also, they can induce corrosion problems, and that can happen in so many ways. For example, the under deposit corrosion in this picture here, or they might, increase the kinetics of the corrosion. That might also, interfere with the corrosion inhibitors you inject into the system, because they can absorb some of the chemicals and then reduce their effective concentration. Also, solids can be a good way to protect the bacteria, because bacteria can live underneath it. And then whenever you inject your biocide or try to, mitigate the bacteria, it's not going to work. Also, solids can cause a huge types of environmental problems. Like, I'm going to give you just a few examples. First thing, we have the norm scale. This is some sort of radioactive material. We also have the pyrophoric iron sulfide. This kind of scale can just, burn whenever it is exposed to air. We also have huge amounts of solids can form in the production system, and you need to get rid of it. This is another problem. Solids can also, increase the CO2 emissions as well, specifically when they deposit inside the heat exchangers or in the treaters or stuff like that. This is going to increase the consumption of the fuel, and then this is going to increase the CO2 emissions. Solids also are related to some fatalities, specifically gas hydrates. We will come to this when we talk about the gas hydrates. And they also there's some connection with some disasters and catastrophes in oil and gas, such as the deep water horizon. We will also talk about this. There's also another case, the Piper Alpha. There is some link. People say they were contributing factors. So we're talking about a huge deal in the industry. It's not just about, blocking a pipeline and that's it. No, it's a huge deal in the oil industry. The main mechanism for solids formation, and this applies to all kinds of solids, of course, with like a few differences, is whenever your material is dissolved into the fluid. It's called a solute. So, but when that solute concentration is higher than the actual solubility of that material, it's going to reach a supersaturation stage. After that, these species are going to cluster up and then nucleate and then reach a specific size called the critical nuclei, and then at that size, they are going to grow in size and form a crystal. The crystal is going to grow up in so many ways, either like a spiral way or a step way, all that stuff. And then after this, the crystal will be flowing in the fluids, and they might reach the surface of the pipeline, adhere to it, and then with time, a layer after layer is going to form. And with the act of the strong hydrodynamic forces and the fluids flow and all kind of different, mechanical force, these layers are going to gain strength, and then it will be hard to remove them. This mechanism is so important, not just for theoretical stuff, but also to understand how the mitigation and the removal of the solids should do, because most of the methods of treating the solids based on understanding that. For example, the chemicals that we inject, the scale inhibitors and all that stuff, they basically interfere with these steps. They interfere with the nucleation crystal growth. This is why we call the scale inhibitors, the wax inhibitors, we call them crystal modifiers or nucleation sequestrant. This is because they interfere with these stages. Or we use dispersants. What they do, they disperse the solid particles, prevent them from adhering to the surface of that of the pipeline. Or some of the internal coating that we put inside the pipeline, they prevent the solid particles from adhering to the surface of the pipeline. We also, some of the magnetic and electromagnetic methods that we apply for the scale or for the paraffins as well, they actually also like interfere with the adhesion step. With the aging step, we use the dissolvers to loosen up the scale layers or remove them from the surface, so we interfere with the aging step. So these are the main steps for solids formation. Our first type of solid that we're going to talk about today is the mineral scales. As you can see, they can block the pipeline in no time. There was one of the cases in the UK, I believe. What happened is what happened is the well blocked with barium sulfate, and the production went from 30,000 barrels per day to zero in just 24 hours because of barium sulfate, in just 24 hours. So these solids can form in no time. They will cause the damage, and it can be a huge deal. So mineral scales are basically linked to the water systems, or the systems that produce water. If you have one of the wells, your water cut increased as of a sudden from, I don't know, 15% to like 30%, 40%, you should be concerned, because the water comes loaded with ionic species, as you can see, very high concentration. And when they meet another water that is not compatible with it, let's say injection water is loaded with sulfate concentration, and then you will have the formation water loaded with calcium or with strontium or with barium, then you will end up with a pipeline or a well or perforation blocked by barium sulfate or calcium sulfate. These are really hard to remove, so you have to be always careful when it comes to scale. What other types of scale we have? We have the carbonate types. We have calcium carbonate, barium carbonate, all kind of stuff there. We have sulfates, we have sulfides, we have oxides, hydroxides. We have also chlorides. Even the table salt, NaCl, can also deposit in a production system, although it has a very high solubility. But because so many things can affect the production, as we will see, and cause scale formation. There's also the suspended solids like sand, clay, and fines. And these ones, we will see, they cause a lot of damages, and they are really hard to predict. They are really hard to see their final effect on production, as we will see later on. We also have the elemental sulfur. What makes what is common between all of these? They all have very limited solubility. like the solubility of barium sulfate is like 2.3 milligrams per liter or something like that. The only one that has a high solubility is the sodium chloride, but that was not enough to prevent it from precipitating, as we will see later on. What are the main impacting factors for mineral scale? So basically we have the mixing of incompatible waters. So as you can see in the picture here, injection water and production or reservoir water, these are not really compatible, specifically with the sulfate and the other metal ions. We have pressure change, temperature change, pH change. We have, if there's a corrosion problem going on in your system, there's microbial activity, geochemical reaction, hydrodynamics of the system that might affect the production and also the formation of scale. We also have the production regime, the gas liquid ratios, and this is a big deal for the sodium chloride, specifically in the systems with high salinity. We also have the fluids composition changes, such as if you are injecting a chemical and this chemical is not compatible with the system, it might cause a deposition of one of the scales, such as the H2S scavengers, the triazines. These can increase the pH of the system, and then this will deposit calcium carbonate. Another thing is you might inject a chemical and it's compatible, but because of the high temperature and pressure, it might decompose. And the decomposition product, it might trigger scale formation. So there's a lot of stuff, as you can see. And the way I listed all that stuff, it's not just to show off or to tell you, I'm just reciting all these factors for you or whatever, but I wanted to tell you a really important thing. That is, whenever you do your risk assessment for scale, you have to consider all of these or most of these as much as you can. I have seen people, whenever they do the risk assessment of their scale, they just get us a water sample, do scale prediction. If the scale prediction showed scale, then there will be scale. If it showed no scale, then we good. We don't need to do anything. And this is when you will get caught. This is one of the biggest problems. The reason behind that is the scale prediction software, they do not include all of these factors in their calculations. They include, yes, they have been a lot of advances, all respect to all the modeling gears and all the modeling softwares, but they do not include all of these factors whenever in their calculations. For example, microbial activity is not there. Geochemical reactions, it's not there. Hydrodynamics, it's not there. Actually, with the hydrodynamics, with the in the scale prediction, they assume that everything that precipitates is going to deposit, and this might not be right. So it might actually give you like overestimation of the problem as well. They do not include the fluids composition changes. I only remember one software type that includes the H2S scavenger problem. It's called Scale Sim. That's why I'm mentioning here, because this is like an awesome change. This is something everybody needs. So again, as I'm saying, whenever you do risk assessment for your scale, you have to consider all of these factors and do not rely on only one piece of investigation whenever you do the risk assessment. You have to consider as much as you can, all the factors, lessons learned from other cases. If you can do experimental studies, all that stuff should be considered. Also, another problem with the, with the scale prediction when it comes to mixing incompatible waters. For example, you might have, let's say you injected water into the reservoir and your system showed compatibility with your production water or reservoir water. That is fine, but there is also another reaction that might not be considered, is the reaction between the injected water and the reservoir rocks. The rocks in the reservoir, there might be anhydrite, for example. So the injected water might dissolve some of the anhydrite, and then it's going to flow smoothly and nicely until it goes up into the tubing and precipitate there. This type of reaction might not be considered in some of the scale prediction software. So you have to be really careful. As I said, consider all the factors whenever you do scale risk assessment. How do we manage scale deposits? So there is this scale management loop. I'm actually going to use this one for all types of solids. So you're going to find the same, graph in all of the coming types of solids. First thing you will have to do, fluid sampling and analysis. So get a proper sample, proper preservation. And then you might need to get the water chemistry, and in some cases you need the hydrocarbons. I actually recommend the hydrocarbons all the time if you can do that, because the hydrocarbons calculations or the hydrocarbons composition might change the calculations in the scale prediction, which we're going to use in the risk assessment here, when it comes to the pH and the evaporation. Sorry about my clumsy writing. So about the pH, the evaporation of the water, and also, the balance between the different phases at the end of the calculations. So sometimes you might need, I recommend it if you can do that. Anyways, you will need the water chemistry, the hydrocarbons, if you can. You need the field data such as pressure, temperature, design, historical data, performance of the current treatments, if there is anything that has been applied. And then you will gather all these data and you will do your risk assessment. Whenever you do your risk assessment with the, scale prediction, you might need to use scale prediction. But in some cases, it might not be enough. You might need to use reservoir simulation as well, specifically if the problem is downhole. And you might need geochemical reactions for that reaction I just mentioned between the injection water and the reservoir rocks. You might need some lessons from other case studies. You need to know more about the actual factors, if there is any bacteria there or not. Bacteria not just cause deposition of iron sulfides. No, bacteria can cause carbonate, different kinds of carbonate, calcium carbonate, iron carbonate, all kinds of sulfides there. All kinds of different scale can happen because of the bacteria. So you might need to, consider the actual factors, and if there is any experimental studies, and then you apply the mitigation, either operational, chemical, or non-chemical. Then you will do the monitoring, as we will see, and then you will watch the system if it's working or not. If it's working, you keep monitoring. If not, you might need to reassess. A few things I wanted to say again about the scale risk assessment. Fluid sampling, always you have to sample the fluids upstream of the problem. If your pipeline having scale, you have to go at the very first point, upstream. Do not collect samples from the downstream, because you will collect the spent water. It's no use. It's going to give you misleading results. What to do with the wells? There's, some options. I know might not be all workable, but there's some options. First thing, you might just sample from the wellhead, and then you use one of the models that can reconstruct the water composition for you. I'm pretty sure there is some of the production, scale prediction software can do the reconstruction of the water. Again, I believe that code scale sim can do this thing. So you might use that one, or you might reconstruct the water yourself. There is a way to do that. You might need to use some calculations to do that, or you might need to do, downhole sampling, and this will be by far the best thing ever you will do, especially if you have a severe scaling problem in one of your wells. Then you will use the modeling. As I said, do not rely on one piece of information in the investigation. You need to do the modeling, and sometimes if the case is in the downhole the well, you might need to do scale prediction, reservoir simulation, and might be some geochemical modeling as well. You might need to use the experimental studies. Just before we go there, so the outcome from the modeling, specifically the scale prediction, will be, the saturation indices of the different kinds of scale. Might give you, the milligrams per liter for each type. Might give you like some indication of how much chemical to use, all that stuff. Besides the modeling and experimental, you might need to look for the impacting factors, as we mentioned, learn from the case studies and analogies and anything else you might need. And then you will take all of this stuff, and then you will put it all these data in a risk matrix and see what is the potential of your scale. How bad is it based on actual and very deep investigation. How to manage scale. So there are so many ways. I just put them into a chemical or non-chemical. You can split the non-chemical into so many ways. In my book, I actually put them in chemical, non-chemical, and operational. So it's eventually up to you, whatever you want to sort them out. So with the operational, basically, I'm concerned about the system, how to operate it in a way to avoid scale formation. Basically, I will improve the design, avoid mixing the incompatible waters. I might need to do like pre-treatment of the water to remove the scaling species, specifically the sulfate. So there is these nano filters here that we can use to remove the sulfate from the seawater or the injection water if they are in a high concentration. We can also use the filtration to remove the solids themselves. We use them in the gas systems to remove the black powder. Anybody has any black powder problems in the field? You might use like, you know, some big filters from a company called Paul. They use like really effective types of filters, but this will remove not the scaling species, but the actual deposits from your system. You might also use coating into like inside the pipeline to prevent the solids from accumulating. Another type is using the physical methods, such as like everybody knows about the magnets. They are very common in the other industries. We call them the magnets. Anything, not chemical, we use it magnets in oil and gas industry actually. But there is so many things. There's magnets, there is electrical methods, there is ultrasonic, and there is electromagnetic method that is actually dedicated to oil and gas fields and has been working for like so many years, and it's showed like huge efficiency. It's called clear well technology. This is this is a picture of one of their cases here. They treat different kinds of scales, specifically the barium sulfate, carbonates, all this kind of stuff. We also use the mechanical methods. We use pegging, coiled tubing, wire lines, but we use this to remove the scale from that has been formed. Chemical methods include the scale inhibitors, either thermodynamic, threshold inhibitors, or dispersants. The thermodynamic ones are being injected in a very high concentration. This is why we use the threshold one, like this one in the picture here, DET, PMP. This is one of the, you know, very efficient types of scale and can treat different kinds scale types. We also use the dispersants, but these are like of kind of like limited use. We use them mostly you know, after the skill inhibitors are not working, or we consume too much of them, and we use them when the skill are in like a fine particles, such as the iron sulfides and zinc also zinc sulfides. Water shut-off chemicals, we use these to prevent the formation that is producing a lot of water from, you know, producing and then we will prevent the water mixing. Then we will prevent the skill problem from its origin. Then we have the scale dissolvers. We use these to remove the scale that has been already formed. So we use different kinds of chemicals. We use the acids for the carbonates and sulfides. We use the packs. These are kind of, you know, chelating agents such as the EDTA. These can remove different kinds of scale, but the main problem with them is that they need a lot of time. And what I mean by a lot of time is sometimes it might take days. So if your system can be, you know, running a little bit slow, if you're not concerned about, oh yeah, we need to, you know, restore the production as soon as possible, if you still have time, you might think about the EDTA. Biocides can be used to remove, you know, the sulfide scale, specifically iron sulfide, zinc sulfide, lead sulfide. Fresh water is used for the sodium chloride. There's also commercial dissolvers, but I don't think there is, you know, a universal dissolver that can dissolve all of these stuff. Some companies claim they have one, but eventually you will have to look at the price of these. How to select a scale inhibitor? There is like a few steps. First of all, you have to do some testing and to determine the minimum inhibitory concentration, or the minimum effective concentration. This can be done by so many ways, but the most effective one is using a dynamic scale loop. This is a picture of it. And then After you test your chemicals, you apply them depending on your system. If you are on a pipeline, mostly will be continuous injection. If you're in a well, there's so many ways, but the most common way is this the scale inhibitor squeeze. We inject the chemical down into the reservoir to protect that the well bore, the well tubing, and sometimes we also give protection to the some of the surface facilities. After we apply this, we keep monitoring of the system to make sure that the treatment is actually working good. How to monitor? There's so many ways. You can watch the system parameters, pressure, temperature, see the productivity, you see the water cut. All that stuff can be indicative of if there's scale forming or not, if the treatment is working or not. You watch the water chemistry, specifically the ions, specific barium, strontium, calcium, iron, zinc, lead, all that stuff. If they are increasing, that means if they are increasing means scale is not forming, or it might be dissolving. If they are decreasing, that means scale is actually and actively forming. You also watch the concentration of the scale inhibitors, as in this picture here. So if your scale inhibitor concentration fell below a specific limit, the minimum inhibitory concentration, then you might need to do a re-squeeze to the system, or you might to check the dose that you are injecting, or maybe there is something wrong with the chemical pump, or maybe there is a lot of solids that are being formed and they just absorb the chemical, so it's not reaching its point. So you will need to investigate in any way. One of the most important and very effective ways of monitoring the scale and can be used to assess the treatment and also assess the risk of the scale is the TSS, the total suspended solids. The reason why is because you can just simply take a sample of the water and then see the TSS over time. If there is a spike in the TSS, that means there is a lot of scale being formed. There is a potential of scale deposition in the system. There should be an action against that. This is a very simple way. Another way is to do, after you finish doing your sampling and doing the TSS, you will get the filter paper, and then you will do more investigation using the electron microscopy and see how much coverage and what is the texture of the scale. Are they actively formed, or they are modified? They are changing in their features and all that stuff, and this will give you an indication if the treatment is actually working or not. You might also use the coupons, either corrosion coupons or scale coupons. There's pools and side stream. You might use some sensors. One of the most effective ones is the tomography. Specifically, you can apply this in the subsea pipelines as well, using some robotics and stuff. It will tell you the scale. Some of them can tell you the scale type and thickness as well. So this is one of the high advances in the sensory stuff when it comes to monitoring systems in oil and gas. You can also use the logging data to see if there is scale being formed or not. Another type of solids is the sand and fines and clay. These can form because of the reservoir mechanics are not really stable. It's unconsolidated. Sand and fine will start also coming out of the system when there's change in the parameters in the system. Water cut is changing, pressure is changing, or because of the design of the well, it's not really proper. Also, they found sometimes the chemicals that we inject into the reservoir, it might cause some damage to the reservoir and cause sand and fines and clay problems as well. So they found too much scale inhibitor squeeze might cause sand production. Same thing for biocides. The water that we inject, if it is with low salinity, it might cause clay swelling, as you can see here. This is also another way, or another problem, because this might not be included in the scale prediction. Another thing is the impacts of these suspended solids. First thing, they can deposit themselves, or they can cause erosion into the production system, the flow lines and the equipment, or they can absorb some of the chemicals on their surface, and then they will reduce the chemical efficiency. And there's also one more thing related to the deposition. that they can deposit on the pipelines or in the production facility, and they can work as a good nucleating sites, you know, for other scale types. They can accumulate on their surface, and then this can trigger scale deposits or any type of deposition. And another problem is this also is not considered in the scale prediction calculations or in the scale prediction models. So you have, again, as I said, you have to consider everything. How to manage scale and fines. Basically, we use operational methods. We use, you know, the screens and gravel packs and all this stuff. We might use also chemicals to reconsolidate that reservoir. Another problem is the gas hydrate. Gas hydrate, like it's been around us for millions of years. Actually, there's some talking that they saying one of the times the extinction happened on Earth because of gas hydrates, a lot of emission of the, you know, methane gas that caused, you know, a big explosion or something that caused some extinction. And this will tell us somehow how dangerous they can be in oil and gas fields. Basically, they are caged-like molecules. So you will have water molecules. They will come together and form a cage, you know, and then inside that cage, it will entrap gas molecules. This is how they form. And this can happen at very high pressures and low temperatures in oil and gas systems. What can they cause in a production system? Can be trivial things, just flow lines restrictions and stuff, or they can cause full blockage of the system, and also they might cause rupture of the pipeline. They might injure some of the operators or might cause fatalities, or they might cause a big disaster like Piper Alpha or Deepwater Horizon. This is how dangerous gas hydrates can be. This is because they have a high expansion power. But before the high expansion power, they can form in very short time. They can form in very short time, and they also have high expansion power as well. The expansion power, people like show it and say, imagine some like a man that is 6 feet will expand to the size of the Eiffel Tower. This is how much power the gas hydrates have. They say you can accumulate 170 times of gas volume in one volume of gas hydrates. This is a lot of power included into the gas hydrates. So they are problematic in production, and they also problematic whenever you try to remove them from the system. So whenever you have gas hydrates, you have to be very careful and always consult a specialist when it comes to gas hydrates. How they form, we basically need the fluids to be you know, at or below the dew point. We need water in the system. If there's surfactants, they might affect the formation. If there's seed crystals there, they will, you know, promote the hydrates formation. What are the conditions? Low temperature and high pressure will accumulate all this together. The water is going to be emulsified inside the hydrocarbon phase, though, and then at low temperature, the water will start to like to form cages like ice and stuff, and then within no time, the gas will be entrapped inside it, and then you will end up with gas hydrates. They might be soft at the beginning, but with time, they are going to accumulate together and form a very hard, like a rocket, you know, like a rock plug that will clog your pipelines and then cause the damage. What are the structures of gas hydrates? We have so many structures. The most common ones are these 3 main structures, but you can count actually up to 7 types, but these are the ones that usually mentioned in the literature, and we can find these two mostly, you can find these two most of the time in oil and gas fields. How to manage gas hydrates? First of all, like you have this loop, as I said, we are going to use this loop, but in the case of gas hydrates, I always recommend to consult a specialist. Always consult a specialist. Maybe not just one person, because this specialist will have his own team, because you will need technical stuff, you will need engineering stuff, you will need safety stuff, as we will see very soon in the removal of the gas hydrates. So first of all, you will have to get fluids data, hydrocarbons composition, water content, all that stuff. You will need to get the field data, production rates, pressure, temperature, dew point, the layout, the historical data, any treatment has been applied or not, and then you will do the risk assessment. Most of the time, the risk assessment for the gas hydrates will be through that prediction. Prediction in gas hydrates is like blood to the human body. You cannot live without it. And then you will apply the mitigation, either chemical or non-chemical, and then you will start monitoring, as we will see now. Something I wanted to mention about the risk assessment, it is really important for the fluid sampling and analysis, as I mentioned, but the software packages, so you have to be like really diligent whenever you pick the software package, because there's some packages will just give you, the hydrate formation zones, like this graph you see here. It's called the hydrate formation or dissociation curve. But there is advanced ones will give you more details, how much chemical you need to inject, if you need insulation or not, and then it's going to give you actually the thickness and the material of the insulation. So if you have a complex field, and this complex field might be vulnerable to hydrate, then you might need to use like highly advanced risk assessment or software package, because it's going to give you a lot of data that you might need. So it depends on the complexity of the problem, and depends on the sophistication of the software package itself. You also might look into the other impacting factors. I'll give you one example. Some of the fields in, I think it was Latin America or something, like whenever they did the risk assessment using the software package, it told them that their system is vulnerable to gas hydrates. But then after a while, they didn't find anything. That's because there was like natural surfactant in the fluids themselves, and then they found that they work as like natural inhibitors, and that prevented the hydrate formation. Some surfactants, on the other hand, can actually promote the hydrate formation and make the problem 100 times worse. And they actually use it, in the carbon storage, CO2 storage, and all that stuff. They induce the hydrate formation by using some surfactants. So some of the surfactants are actually friendly, some of them are really, really evil. So you might also use experimental studies. You might need, the rocking cell, the autoclave, all this kind of experiment, the flow loop, all this kind of stuff might be very useful. You will need to listen and learn from, the analogy and the similar case studies. They have a good experience in dealing with gas hydrates, because, as I said, gas hydrates is not something trivial, is not something easy. Yeah, it might be working for a bit, but if anything goes wrong with them, it will be very, very dangerous. And use anything else you can use to mitigate gas hydrates. How to manage gas hydrates? There's so many ways. Again, chemical, non-chemical. The non-chemical might have operational methods. First of all, just remove the water from the system. Get rid of it. How is that? By doing gas dehydration. Do it properly. How to do gas dehydration? The very convenient or conventional systems that we use. You might add some units if your system is very complex. There is some dehydration, like subsea dehydration. I mean, these might be useful if you have really bad hydrate problems, or you might use another technology called the cold flow. So the cold flow is a way to do gas dehydration from one point, and on the other point to mitigate the hydrate if your system is have severe hydrate formation. The cold flow is basically will induce the hydrate formation, but in a way that is not going to clog the system, but will keep moving like a slurry. So this is your pipeline. It's going to make it as like particles suspended in the flow, and they will keep moving. They're not going to accumulate until you reach the surface, and then you can deal with this in a better way. Another way to mitigate this is using the internal coating. You will have to do pressure control. One of the methods to control the hydrate is to reduce the pressure, so it's below the hydrate formation pressure. And it's also a way to remove the hydrate plugs. It's called depressurization. We'll talk about this later on. Another way is to improve the design as well. Another method for the management is the thermal method. This is a way of temperature control. This can be done in a passive way, such as the insulation, or the active way, such as the active heating. So many technologies right now in the active heating. There is, the tracing. There is, piggyback and all that stuff. There have been advances. They can be applied in the subsea pipelines because these ones are the worst. And again, this should be part of your risk assessment in the FEED stage of your field, because you might need to, like, instead of like modifying your system and doing everything all over again, if you do this in the early stages, this will save you time and money as well. Another way of managing hydrate is through the mechanical methods. There is pigging, coil tubing, and wire line. The pigging is usually used for two purposes. If your hydrates are soft, they're not really hard, they're not clogging the pipeline totally. If there is a communication between like the two sides of the plug, you might be able to use the pigging. But if there's the plug already there and it's long, do not use pigging, because this might either break the pig, it's going to like make the problem worse. You might, make the plug itself harder to remove afterwards. But the best thing we use for the mechanical is the coil tubing. That's because we use the mechanical force in it. We also can use chemicals, and we can heat up we can also heat up the chemicals as well, and this is going to improve the removal. So coil tubing is actually one of the main pieces to control the gas hydrates. One last thing also about the pigging, we can use the pigging also for gas dehydration purposes. If your pipeline, there's water pools or anything in there, if there's, you might like run a pig couple times to dry the pipeline. This might improve, and prevent the hydrate formation. Chemical methods, we have the thermodynamic types of inhibitors. These are usually injected in high concentration, up to 60% of the water cut. And then we have another type that we can inject in a low dosage. It's called low dosage hydrate inhibitors. We usually inject these in a smaller concentration, 1 to 3%. We have two types, the kinetic and the anti-agglomerant. Once the kinetics will give you more time before the full blockage is happening, until you reach the surface or reach to a spot that you can mitigate it better. The anti-agglomerants will give you even more time, and they will keep the hydrates, suspended, and this will cause no problems. To summarize how the hydrate mitigation methods work, the prevention is basically, if you look at this chart here, we have the hydrate formation curve. Whenever we apply chemicals, specifically the THIs, it's going to push this hydrate formation curve a little bit to the left. So your production profile will be outside the hydrate formation. Then you will be safe. If you are, applying, the depressurization method or using heat, what are you doing is actually you are working your operating conditions outside, the hydrate formation zone, and then you will be also safe from the hydrate problems. The removal methods on the other side, I wanted to mention and point this, and this is really serious. Whenever you have a problem, a plug of hydrate, you always have to consult a specialist team, because there's safety issues, technical issues, engineering issues that need to be considered. One of the things is for the removal is the depressurization, and this should be always done from two sides of depressurization, because if you did one-sided depressurization, what's going to happen is, partially around the pipeline surface, the hydrate plug will dissolve. And because of the expansion forces that we mentioned about the hydrate, this is too much force. What's going to happen is there's going to build a lot of pressure on the back of the hydrate plug. And then once it is loose to move, it's not just going to move. It is going to shoot like a rocket, and then it might rupture the pipeline. And if there is like people around the pipeline or something, someone might get hurt, someone might, get killed. And that there was actually a lot of cases people reported dead because of the hydrate plug. They call it the hydrate projectile. So that's one of the things that you should consider whenever you mitigate dehydrate. Always use different methods altogether. If you can use mechanical, chemical, and operational methods, use all you can. They usually ask you to fill the line with, THI or something to work as, a cushion to absorb any shocks that can happen if there's any pressure buildup or something. And if by any chance the hydrate plug went flying into the pipeline, it'll absorb it and then will reduce the impact on the pipeline. If you can use coil tubing, it will include the mechanical force, the chemical force, and also the thermal force, because you can inject things a little bit warm inside the coil tubing, and this will improve the dissolution of your gas hydrates removal. How to monitor gas hydrates? Basically, you watch the system parameters, pressure, temperature, productivity. There is a technique that is called pressure pulse that has been used in Europe for so many years to watch. Actually, they can use it to locate the plug of the gas hydrates. There's also the dew point. You have to watch the dew point. You watch the gas composition, and it changes can be indicative of hydrate formation. You watch the water cut. If the water is coming in your pipeline less than it used to be, that means the water has gone somewhere, and the obvious where is into hydrate formation. So you have to watch for that. You can use some sensors, specifically, again, the tomography, that can be very handful, specifically in the subsea pipelines. There's the pigging operations, as we said, you can use them to remove the soft accumulations, and you can also use it to, monitor the system and also to dry the system to prevent the hydrate formation. You can use the prediction. As I said, prediction in gas hydrates is really, really crucial. Another problem we have is the paraffins. So paraffins are basically one of the fractions of the crude oil. When you look at the main fractions of crude oil, we have saturates, aromatics, resins, and asphaltenes. Paraffins belong to the desaturate fraction. They are high molecular weight alkanes. Some people mention they are higher than C15 of composition. Some people say C20 plus, C25 plus, but it is different from crude oil to another. So you have to figure this out for your own crude oil. Do not just rely on historical data. You have to do experimental work and see what kind of paraffins in your hydrocarbons can be problematic. Paraffins are always related to the temperature change. Whenever we talk about this, we talk about two types of temperature. There is the wax appearance temperature, or the WAT. There is also the pour point temperature. So the wax appearance temperature, this is the limit. This is kind of like the solubility limit of the waxes. So if you look at the picture down here, whenever the crude oil is coming hot enough from the well, and then in its way, some cooling is going to happen because of the heat loss to the surrounding environment. And then when the temperature gets at or below the wax appearance temperature, wax crystals are going to drop off the system. And then with continuous heat loss, more and more of these will continue, to drop off, and more of the flow will get restricted, and then you will hit the pour point. This is when the flow of your crude oil is actually going to stop. You will see this. You might find your crude oil pump is not working anymore. Your pipeline is like partially clogged. Pressure is going down. Productivity is not going well. So you have to check the temperature. You always have to take the temperature profile of your system. Make sure that your crude oil can flow within this temperature profile or not. How waxes deposit? There's so many mechanisms. I'll take the first one, the molecular diffusion. This is considered the common one, or the one that everybody considers the main mechanism. So if you look at the pipeline here with the waxes, this is the pipeline wall. At this pipeline wall, let's consider the temperature reached the wax appearance temperature, or the WAT. What's going to happen to the wax crystals or the wax molecules near it? They are going to deposit. But then the wax molecules near the bulk, or in the bulk of the crude oil, they are still hot enough, so they are still dissolved. But because of the difference in the concentration between the bulk of the crude oil versus the pipe wall, then these high molecular weight, or the paraffin high molecular weight molecules, or the high molecular weight paraffin molecules, they will, you know, diffuse from the bulk of the crude oil to reach, you know, the pipeline surface. But at this case, they will hit, you know, the wax deposit layer because too many wax crystals are already in there. Once they hit there, there will be more diffusion. They will diffuse into inside this wax layer. We also call it the gel layer, and then the oil will come out of that, and then it's going to start to solidify, and then it'll be hard to remove after time, and then will keep accumulating until you end up with a wax plug in your pipeline. There's always another mechanism. There is Brownian diffusion, there is shear dispersion, gravity settling, shear stripping, thermal diffusion. So which one will take the cake? Most people talk about the molecular diffusion, but in actual cases or in actual field conditions, any one of these can be the main mechanism why waxes are usually deposited. But this one, the molecular diffusion, could be the main mechanism. And I listed these mechanisms here for a purpose, because the modeling software for waxes, they might consider one or two of these mechanisms, but they may not consider the others. So, for example, some wax models, they only use the shear dispersion as the main mechanism for wax deposition, and they do not consider the rest of these. Other ones might consider the molecular diffusion as the main mechanism. So whenever you use a wax modeling software, you have to do a little bit of reading which mechanism they're using and see what's your system is actually like. If your system, is there a big difference in the temperature in your system or not? What's the composition of your fluids, and what's the paraffin waxes look like? What's the carbon number distribution on them? So what's the impacting factors for the wax? First of all, we have the temperature. This is the main factor. Whenever we talk about the temperature, there's so many things. So first of all, we have the wax appearance temperature. This is the minimum limit for solubility. This is and then we have the pour point. This is the limit for the flowability of our crude oil. But we also have the environmental or the surrounding temperature, or the outer environment temperature. So we're going to give it TS. And then we have the pipe wall temperature, TP. And then we have the bulk temperature. So this is going to be TB. Is that all? No. We also have temperature gradients, delta T, and this can be like along the pipeline. So let's say you have the well coming from here and your flow is coming this way. There will be always like differential temperature along the pipeline. Let's call it like delta T axial. And then we will have a delta T radial. This is the temperature difference across the pipeline. So there is so many temperature factors here that you should consider, because if the temperature of the surrounding media is very, very, very low, it's going to make the delta, so let's call this delta T here, sorry, delta T radial. It's going to make the delta T radial like very, very big, and then this is going to cause the waxes to deposit from the system like very, very quickly. Same thing for the axial. Like if your system going a long distances, then you might have to check on so many different spots, because you might find waxes depositing there in so many different ways. You might end up with a big plug at the end of the pipeline. So you have to consider the wet, the pour point, but also you have or you need to do survey on the surrounding media temperature, the pipeline temperature, the bulk oil temperature, and you see the temperature gradients across these. And if you have insulation, you also need to check that one as well. The other factor is the pressure drop. I'm going to talk about the Joule-Thomson cooling. This is when your system has gas and then it's going to flow through some restrictions, and then this is going to, drop cause a drop in the temperature. And if the temperature fell below the wet, this is going to cause, deposition. Another problem with the pressure drop is that you are going to lose the light ends, and these work as the solvent for the wax molecules. This is another problem. Another thing is the oil composition. If you have high concentration of the hot high molecular weight waxes, it might be a problem. If you have asphaltenes, it might be also a problem, because sometimes asphaltenes can work either as promoting for wax deposition, or they might work as, you know, inhibitor for wax deposition. It depends. So you might need the oil composition as part of your risk assessment. Also, you need to know the hydrodynamics. This is what we just talked about. If you have a long pipeline and there's like a temperature, a strong temperature gradient across this pipeline, you might need to check your hydrodynamics. If the flow is enough to, you know, carry the wax solids across the pipeline, and where are they going to accumulate? And this will give you an indication of where you should inject your chemicals and how many times, or how many chemicals that you should use. How to manage the waxes. So first of all, we have the fluids chemistry. We need to know the hydrocarbon composition, Sara analysis. PVT is important. Wax appearance, temperature, pour point, you know, viscosity, density. We might need to do some experimental studies. This will be part of your, you know, risk assessment, as we will see as well. You need to know the field data, pressure, temperature, layout, the historical data, performance of the current chemicals. And then you will use all of that to do, you know, solid risk assessment for the wax deposition using the prediction and modeling. Or maybe you will use some of the experimental studies, and this is what I was going to talk about here. So the experimental studies, actually, there is a lot when it comes to the wax. So you can do like simple test, like the wet test. Then you can look for the pour point. You can do cold finger. This is very common. You can use the wax flow loop. There's a lot of stuff you can do, you know, when it comes to wax. And some of these are really easy. You can use them and add them to the outcomes coming from the software packages, and then put all of this, again, as we said, into a big risk assessment matrix and see if the wax is going to form or not. One thing to mention about the fluids sampling and analysis, you have to sample, like everything else, upstream of the problem. So how to know that, or where exactly is this? This will be temperature dependent. So you have to be upstream of the wet. How much? As far as you can. Some people say 10, 15, 20 degrees further up from the wet. This should be the best part to, you know, get a representative sample. How to manage the paraffins? There's so many ways. Chemicals, or non-chemical methods. The non-chemical methods, you might need to, you know, improve the flow, or you can use the cold flow. That one is similar to the gas hydrates. You might need the internal coating, pressure control, or the thermal methods. This is used very similar to the gas hydrates, using either insulation or active heating. You can actually also model these, use as part of your risk assessment. Like the software packages, it's going to give you the wax deposition envelope, and also might give you like an indication of the necessity of the insulation or the heat, how much chemicals you might need to use. So the thermal methods can be part of your risk assessment as well. And then you will use mechanical methods to remove the wax deposits. There is the pigging, cold tubing, the wire lines. Pigging need to be really, really optimized, because you might you might have a wax plug that is easy to move, but because you use the wrong pig or the wrong pigging operation, and then you will end up with a big, solid, hard plug in your system. So the chemical methods, we have the paraffins. For the paraffins, we have the paraffin inhibitors. We have the pour point depressants, we have the paraffin dispersants, and also we have the solvents. You need to determine which one to use based on your chemical testing, and also based on your system design and the thermal history of your samples. Because if you collected a wrong sample and you are trying to achieve a specific wet or a specific pour point? I get these questions all the time because people get sample and then they add the chemical, and the wet or the pour point they're trying to achieve is not achievable. That's because you collected the wrong sample. So you have to look into the thermal history, because if you heat it, if the crude oil has been heated somehow using heaters or heat exchangers, it might change the wet value and the pour point value. So the samples that you are collecting might not be actually representative. So you will do testing and selection of the chemicals using the pour point, the wet, the cold finger, the flow loop, and then you will apply them. Mostly will be using continuous injection, will upstream of the wet based on the system hydrodynamics, and then you will monitor the system using, you know, the production data or using some lab tests like viscosity, wax appearance temperature, pour point, or the crude oil composition. If there's a drop in the wax, that means wax is actually depositing. If wax is going high again, it means either it's dissolving or it might be not precipitating, so your system is protected. You might need you might also use the coupons, the sensors, such as the tomography. Again, this has been like the champ for oil and gas. You might use the pigging data to see if wax is accumulating or not, or the well logging to just to check what is going on in your system. Uh, I got a request to stop the next one we have. So the next one we have here is the asphaltenes, as we mentioned earlier. So asphaltenes is one of the biggest problems in oil and gas fields. They are called the cholesterol of oil. They are a fraction of crude oil. They darken color. They high molecular weight. They are the heaviest molecules in crude oil. They have elements such as carbon, hydrogen, you know, sulfur, oxygen, nitrogen, and they also have metal ions such as nickel, vanadium, iron, all this kind of stuff. They basically insoluble in alkanes, but they are soluble in toluene. They have high molecular weight somehow. It can range between 500 to 1,000 daltons. Their composition, as you can see here, they have like polyaromatic cores in the middle, and then they will have side chains as well. They might be connected like different cores together. It'll call like the rosary type or the rosary structure, or they can be all in one core, and this will be called the continental structure. What can they cause in the system? They can cause, you know, formation damage. They change the wettability of the formation, a change, and then this will like decline the production in no time. They might cause, you know, flow restrictions. They might stabilize the emulsions, and this is what they are famous for. How they exist in crude oil? The very first and well-known theory about this is that they are stabilized somehow by the resins, and you know, the resins are kind of like absorbed around them, stabilizing them, and this is how they will be dissolved in crude oil. Another model, which is like considered the last model of seeing asphaltenes, is the Yin-Mullins model. They can be as like single molecules dissolved in the light crude oil, or can be nano aggregates in the black oil, or, you know, clusters of nano aggregates in the heavier types of oil. How they usually like deposit in the system, it's kind of like hierarchical way of depositing. So the single molecules will aggregate into nano aggregates, and these nano aggregates will cluster up to form clusters, which will flocculate into primary molecules, and then they will, with time and hydrodynamics, they will deposit in the system. What are the main impacting factors of asphaltenes? We have the pressure drop, which is the main thing, specifically when you hit the bubble point or near the bubble point, something called the asphaltene onset pressure, and then they will keep accumulating and precipitating until they hit their highest amount of precipitation will happen at the bubble point. There's also the temperature change, pH shift and acidizing, incompatible fluids mixing. This includes crude oils, or could be alkanes, or could be CO2, or could be the gas lift. anything like this can destabilize the asphaltene and cause their deposition in your system. So many things can affect the asphaltenes. Also, the crude oil composition. If you have high resin, that might stabilize the asphaltenes. If you have high alkanes and then somehow the pressure drops, this might destabilize them. We use this formula. It's called the colloidal instability index, or the CII, will indicate if your crude oil is stable or not, and this is easy to achieve. We also have the shear and hydrodynamics, and we also have the streaming potential, and corrosion problems can be a huge deal when it comes to asphaltenes. So there are so many things whenever you look at the asphaltenes. This is why every time I talk about them, I love this photo because it represents the asphaltenes. From some way, they are really elusive, like DiCaprio in his movie Catch Me If You Can, you know? He's really elusive, really tricky. You cannot really predict his next move. Same thing for asphaltenes. And they're also like very sensitive. They are bulky, big molecules, but they are so sensitive to so many things in the system. And they're kind of like this guy. He's kind of like absorb the suffering of people, right? Asphaltenes is the same thing. It's trying to absorb, you know, the changes in the system, and then they will do another thermodynamic equilibrium, and then they will precipitate. How to manage asphaltenes? Basically, you will do fluids chemistry, and then you will gather the system data, do a risk assessment, and then apply the mitigation and monitor that. Whenever you do the risk assessment, you can do this by a lot of lab work to measure the crude oil composition, PVT, SARA analysis, different fractions. Very important things is the asphaltene onset pressure and the bubble point. These are really crucial. You can get these from the PVT studies. And then you will do some risk assessment using some, easy, relations such as the CII or the resin to asphaltene ratio or deep wear, method. There's also the software packages that you can use. You can do the experimental studies using different ways, either flow loop or the flocculation of the asphaltenes. There's some historical data that you can use to achieve a proper risk assessment. How to manage asphaltenes? So there's operational ways. So you can improve the design, avoid mixing the different crude oils, use internal coating. You can do a pressure control. You can also like optimize the gas lift operations. There's physical methods. These are not really chemical, are not really common. There's also mechanical methods. So like you can use pigging, coiled tubing, wire line. There's also the chemical methods. These can use the asphaltene inhibitors or dispersants or some solvents, but whatever you inject there, make sure it's compatible with your crude oil. They should be mostly like surfactant wise or aromatic wise, to prevent the destabilization of your asphaltenes. How to test the asphaltene or how to apply the asphaltene chemicals. So you'll do some testing for the chemicals, make sure they are representative. You apply them. Most of the time will be upstream of the asphaltene onset pressure. Squeeze jobs have been used like recently, but they do not show like high success ratios. And then you will do the monitoring after that to see if the chemicals are working or not by monitoring the production data. See, also you can do some lab tests like viscosity, asphaltene onset pressure, if it's changing or not. Turbidity test, crude oil composition to see if there's any changes or not. There's also the coupons, the sensors, such as the tomography. There's also the pigging data and the well logging. All that stuff you can use. Another type of solids we have here. Sorry, I'm just running so fast so we can finish on time. Sorry if I made everyone late or I went like over the time. So the next type we have here is the naphthenate soaps. These have been like discovered recently. These are based on the reaction between the naphthenic acids and carboxylic acids and the crude oil with the water, specifically at high, not really high, relatively high pH. They say pH has to be above 6 to start forming these naphthenate soap. So the naphthenic acid will dissociate, move to the water interface, and then it's going to deposit whenever it reacts with the metal ions in the water. Some of the impacting factors are the crude oil composition, if you have a lot of naphthenic acids, the water composition, specifically the metal ions, calcium, magnesium, iron, sodium, all that stuff, the pH, if it is higher than 6, the alkalinity of the system. If you have high alkalinity, that means you will have high chances of soap formation, mixing of incompatible fluids, especially if the crude is high in naphthenic acids and the water is high in the metal ions. Pressure change is one of the biggest triggers for the soap formation and the temperature change for sure. How to manage the soap? You will do fluids chemistry, um, uh, water composition, crude oil composition. Then you will use the field data. You'll do the risk assessment, and then you will apply the mitigation. The mitigation methods can be operational by improving the design, avoid the mixing, do add like more washing tanks, diluting your fluids. The mechanical methods basically are pigging, coil tubing, wireline, or you can do this manually if they are forming in the bottom of the tanks or in the separators or stuff like that. Then we have the chemicals are basically based on the use of acids. Even if you are using demulsifiers, most of the times they will have to be acidic demulsifiers, or you can use some of the strongest naphthenate inhibitors to avoid the naphthenate problems. How to select that? You will have to collect a representative sample, do some testing. There is like a naphthenate rigs or mini loop that you can use to do that, and then you'll do continuous injection in the system, and then you monitor this production data, and then some of the equipment performance, specifically the separators. And then you will do some lab tests to see the ions concentration, the pH, the oil acid number, and then you will do a lot of samplings from the interface. This is really important, or use sensors and coupons, production and logging data. Then we have a mix of all of the different types of solids. It's called the shmoo. The shmoo is basically a sticky, smelly material. It's made of like a mix of organic and inorganic material. You can see here they have scale, asphaltenes, waxes, biomass, sand, clay, all kind of stuff there. They restrict the flow and they impact heavily the injection wells. They can cause corrosion and bacterial activity, and they affect the chemical efficiency because they absorb like a layer coating inside the pipeline, and this will make any chemical you inject not really working. The mitigation of the shmoo can be by basically the pigging or using some surfactant to disperse that layer. Where the word shmoo is coming from, I think it's coming from the German word of schmutzdicke, or whatever the way they say that. It's used in the sand filters and in the filtration systems. It's made of organic and inorganic biomasses as well. I think somehow someone shortened that down to schmutz, and then we just starting to say shmoo instead of like using the German bold, bulky word schmutzdicke or schmutz. We just say shmoo for simplicity. That's my theory. Might be the right thing. Now we're going to move to the phase separation problems. You have so many stuff such as the emulsion, the foam, the sludge. Phase separation problems are highly related to the solids because solids can accumulate in the facilities, in the separators, reduce their size, that's one thing, or foul the internals of the separator, which might make it really not highly performing, or they will destabilize, they will stabilize, the emulsions, and then this will make them hard to deal with, or they might, absorb some of the chemicals that you inject, and this will make the separation problems even worse. So this is why I picked these two topics to be all together. The first thing we have is the emulsion. When you mix oil, water, and presence of emulsifying agent and you have agitation, then you will have an emulsion highly stabilized by different kinds of emulsifying agents. As you can see, there is a tight emulsion, there is loose emulsion, depending on the composition of your fluids, the degree of agitation, the pH of the system, the oil properties, density, viscosity, the water salinity, how much water you have, the density of the water, all this kind of stuff. How to manage the emulsions? You pick samples, especially interface samples, analyze them, get the oil sample, do the Sarah analysis, viscosity, density, get the water, see the pH, TDS, all that stuff, and then you will start to do risk assessment by, do stability of the emulsions. Try so many ways to see how to break them. So how to deal with the emulsions? We basically have equipment, so like separators, cyclones, heater treaters, desalters, all this kind of stuff. So all of that stuff will be used to deal with the emulsions. But the most commonly thing used besides these equipment is the chemicals. But to apply the chemicals properly, you need to do a proper selection of that. You will get a sample, you do bottle test, and then you will do a field trial to determine the gallons per day. Then after a while, you will optimize this, and then you will go down with the dose, and then you will know what to do with the solids. After that, you will monitor the system. You will look into the water cut, the separation on the vessels, if it's going good or not. To do a good risk assessment for the emulsions, you need to know the root cause. Is it like asphaltenes? Is it solids? Is it naphthanates? Is it chemicals that you are injecting? Why the chemicals are not working? If you are already injecting chemicals, if everything goes all right, but the retention time in your vessel is not okay, is your vessels actually the right size or not? Is the inlet, is it foam has something to do with it? So all that stuff you might need to look into whenever it comes to the emulsifiers. We use the oilers as well for the water treatment. Sometimes we might need to use the solids chemicals, because if the root cause is related to the solids, then you have to treat the solids before you go anywhere with your system. Another problem is the foam. It's another form of a colloidal state, but it's a gas in liquid. If there's any surfactants to stabilize that, it depends on the fluid's properties, and also depends on your vessel properties as well. For example, if you have a vessel and then your vessel somehow the fluids are coming in causing foam, what's going to happen? The foam might cause liquid carry over into the gas phase, and this is going to damage the treatment facilities after that. Or it might cause gas carry over into the liquid side, and then this is going to cause problems in the oil treatment facilities as well. So you have to be very diligent when the foam to deal with the foam. We basically have to do the right sizing for your vessel, improve the inlet, improve the internals of your vessel to make sure it's going to break the foam. Also, you might inject some chemicals. These chemicals has to be injected at the inlet of the separator so that it's going to break the foam. Most of the time you will have anti-foam or defoamers. And then we have the sludge. This is another of colloidal state, but is in a hard form. Mostly it's oil, sand, solids, a little bit of water, all emulsified together in a hard way. They form in the tank bottoms, in the separators, in the dead legs, traps, in the vessels as well. You might need to remove these manually, in fact, and then sometimes you need to dissolve them before you go anywhere, and you don't have to recycle them back into the production system, because they might impact your phase separation or make your desalter go high in the salt. So you have to be understanding what these can cause whenever you deal with them. You can deal with them mechanically, as I said, or you can inject some anti-sludge chemicals, or you can use the solvents to loosen them up before you do anything. What to consider whenever you do the flow assurance or the production chemistry? As I said, I'm going to go back to that table again. I'm asking everybody to have the same table for your wells or your production system. See what's the parameters you have, what's the fluids you have, what are the possible reactions you might need to that might happen between them, and then put all of this together, and then you might have a good risk assessment with anything or any potential production chemistry problem in your system. So that's all about this webinar. Sorry for taking too long time, and the speech is all yours.